for attending. My name is Rami Abielmona. I'm the VP of Research and Engineering at Larus Technologies. We're a Hexagon strategic partner, hence why we were invited to present today. Today I'm going to talk about ensuring all domain awareness according to AI, ML-driven big data analytics. So we're based out of Ottawa, Canada, as you see there, the capital of Canada. And thanks again for inviting us to this Geoawesomeness Digital Meetup presentation. So just a quick brief overview about Larus Technologies. We were established in 1995. We're a wholly owned Canadian engineering product company, over 25 years of experience in defense and public safety awareness systems. We specialize in predictive analytics and decision support systems, specifically using AI and ML for national public security safety systems, all domain awareness, and C2, C3, C4 ISR systems. We're recognized leaders in AI, ML, and information fusion research and product development. Back in 2015, we won the AI award. It was called, it was still called the Computational Intelligence Society in the IEEE, but we got one worldwide for 2015. 2016, we got one in Canada from NSERC. In 17, we got one from NATO, from NCI specifically, and just this past year, the Ottawa section recognized us as the most outstanding high-tech company here in Ottawa. So just quickly about our team, we're very proud of our team. We're about 25 people, but the top right figure there is probably the most important thing. 15 of us have PhDs and masters in what I call wide artificial intelligence. So this is not just deep learning, but evolutionary computation, genetic algorithms, fuzzy systems, applied to various problems, including computer vision, natural language processing, time series prediction, classification problems, multi-objective optimization, and so on and so forth. We publish a lot of papers, so you can track us across ResearchGate or IEEE Explore, whatnot, specifically papers that have to do with AI, ML as they are applied to security and defense. We've co-founded some groups as well. CTFG is Canadian Tracking Fusion Group, but the other two acronyms may be of interest. CISTA specifically is the Computational Intelligence Workshop for Security and Defense Applications. It's an IEEE workshop that's run all over the world. We just finished a virtual event in 2020, but we are planning hopefully in-person ones later this year. We have three main products on the market. I'll kind of talk about all three of them today. Total Insight is on the left. It's our decision support system that uses AI and ML and brings together all elements of analytics, data analytics, to provide kind of real-time decision support. Total Perception is a modeling simulation, system simulation engine that provides multi-objective optimization and plays out what-if scenarios to answer various questions, mission planning questions, response planning questions, collection planning questions, and so on and so forth. And Total Vision is a computer vision product that allows us to detect, track, classify objects and events of interest. So just quickly going through Total Insight, it is a patented product in the USPTO. It was issued to us in 2013. It involves multi-layered information fusion, including situational assessment, where we take in all kinds of big data and perform information fusion on the fly, and then we can then apply higher level analytics, things like classification, prediction, association, anomaly detection algorithms. Impact assessment is next, where we perform risk management, response generation, and situational learning. And finally, process refinement, where we perform a lot of resource management and procedural learning is the last layer. So what are some big data issues? Brian will probably attest to this, and anyone else has used Luciad. So lots of data in front of operators. This is typically a common operating picture that's flooded with contacts and tracks. This is the Malacca Straits, one of the heaviest and most congested waterways in the world. And the idea here is which red dot belongs to and green dot belongs to which blue track, basically. So that's called the track fusion or the tracking problem. And after you've done that, then you kind of want to simplify or reduce the clutter for the operator by pointing out kind of suspect and illicit kind of activities. Things like illegal fishing or dark targets or rendezvous or bunkering that is not allowed if it's not been licensed, and so on and so forth. So these are the types of activities that one would want to fish out. It's kind of really looking for needles in a haystack, but you're looking for a bunch of needles in a lot of haystacks. A bit about impact assessment. So layer 2 is all about anomaly detection, a risk assessment, threat assessment, and once you understand kind of what the entities are and how they relate to each other, and in the scenario that's at hand, then you can kind of move up to layer 3, and here you're doing a lot of impact assessment. So what you want to do is, from the same environment, using very similar sensor data, you want to start extracting risk features, so machine learning algorithms in the background and AI algorithms extract the risk features, assess the risk, and AI algorithms generate the responses. So all this is done using various AI algorithms. Again, deep learning and neural networks will work for certain types of problems, but not all problems. So here's just a demo that we did in the Gulf of Thailand, where we brought in space-based AIS as well as littoral AIS. AIS is automated identification system that basically allows different vessels around the world to kind of advertise where they are and where they're heading and their status as well, both in static and dynamic fashion. We also brought in some local data from the Gulf of Thailand. We also brought in soft data from that area. Soft data being reports, incident reports, collision reports, and vessel distress reports, and so on and so forth. We fuse all that within one of our lower layers within Total Insight, and then in layer 2 we start identifying vessels in distress. So in this case, we want to predict a vessel in distress from all these different vessels. I think there was about 30 in that environment. And then once we've predicted a vessel in distress, we also want to use AI to generate the best course of action in layer 3. So what is the best response to that event in real time? So as you can see here, there's about 3 different kind of triage stations inland around the Gulf of Thailand. And the idea is that to run the real-time data and extract risk features that were generated using ML algorithms. You can see them on the top right there with collision factor, sea state, degree of distress, and regional hostility metrics being the ones that were most useful. We want to run kind of prediction algorithms. So there's kind of a clustering algorithm that uses unsupervised learning to cluster the data together and telling us in the end the overall risk upon all those different entities in the scenario. You can see that there's 2 particular vessels that breach the user set threshold, which was 0.96. They're actually 1s, which means they're exhibiting data that other vessels have exhibited in the past that have actually gone into distress themselves. So in this case, we pick one of the vessels, the oil tanker 4. We say that's our vessel in distress. Again, this is a prediction. And then we hit optimize responses. Another class of AI algorithms runs. And you can see within less than a second, we've got some courses of actions. Here we call them response chains. And you can see, you can click on chain 1, which basically says, okay, well, oil tanker 4 can transfer goods and people to speedboat 3, to tugboat 2, to medical vessel 2, and eventually to the Donsock Hospital with costing in the background. There are costing models, there's movement models, and other models that are running in the background. And you can see the objective functions. This is a multi-objective optimization algorithm that tries to, in a non-dominant fashion, generate various different options for the user. So here you can pick kind of the slower response, but it's less costly, or a faster response, but it's more costlier, obviously, with a higher casualty probability for that matter. Total Insight provides a slew of capabilities. We don't really have the time within 15 minutes to kind of cover them all, but just a smattering of capabilities here. Top left, we can generate heat maps, obviously based on our data sets and our both raw data sets as well as derived data sets, so kind of density heat maps around the world. You could do anomaly heat maps for certain parts of the world. So this was in August last year, anomaly heat map for dark targets. So you can see the red cells around the Strait of Hormuz where vessels are kind of turning off their AIS transponders on purpose for reasons that we all know, kind of it's dangerous waters there. In the top row, middle column, you've got an unsupervised AI algorithm that can learn based on data any shape of an airport, a maritime port, a critical infrastructure, just by data with no human involvement there. Bottom left is kind of Google Maps, but on water, where you take kind of raw data. We run machine learning algorithms to extract information, things like routes and trends, and eventually are able to track corridors, geospatially aware corridors, so we can run these seasonally and compare them from season to a season without having any digital maps or humans involved. And then bottom right is radar processing. So we have deep learning algorithms that within less than a second can identify with radars, especially highly sensitized radar in the defense and security realm. The reason why they're highly sensitized is because they want to catch kind of smaller entities that evade or don't have to transmit certain on certain channels, like small fishing boats and so on and so forth. So the problem when you highly sensitize the radar is it catches everything else, flocks of birds, multipath effects, cars over bridges. So we built out and trained a deep learning algorithm that tells you whether that particular track is coming from a point-based entity, a vessel or a vehicle or an aircraft or whatever it is, and can obviously rule out the nuisance if need be. We've been partners with Hexagon for a couple of years now. We've integrated Total Insight within Luciad, which Brian already discussed at length. So I'm not an expert in Luciad, but I can tell you what we did with Luciad RIA and Luciad Fusion. But another one that we're integrating in currently is Exalt, which is kind of a messaging bus that allows us to transfer information from different systems. So imagine kind of your data coming in from the left there with vessel tracking data, assets data, inventory data, weather data, historical data, and so on and so forth. That all goes through Exalt, and that's where we grab our data from in Total Insight, generate our kind of anomalies and predictions and assessments and COAs, and send those off to Exalt so that we can pop them up on Luciad RIA, or to send them to another system, which I'll talk about, which is Total Perception, for more modeling and simulation experimentation. So we've integrated with actually a couple of visualization frameworks that Hexagon as a company offers. One is SmartMap Enterprise, which you're seeing here. We took one of our data sets, both fuse tracks as well as anomalies, and worked with Hexagon to integrate that within SmartMap. And you can kind of see here some really interesting analytics in terms of wanting to see, you know, the time of day in terms of the number of entities that appear in the time of day, a live heat map that's generated, whether you zoom in or zoom out into the actual I don't know if the video, oh yeah, I stopped it by accident. When you zoom in and out, you can actually see, you know, the number of entities changing and the number of features changing. You can have kind of updated pie charts in terms of navigation status. You can search by the identifiers, which are called MMSIs in the maritime world. And of course, you could have, you know, speed graphs and date range graphs and so on and so forth. You can visually inspect kind of specific entities, and whether it's a contact or a particular track, and all that is linked to, you know, images from other systems. All that is brought into the SmartMap Enterprise application and can be visualized in a very seamless fashion. As I mentioned, we've integrated with Luciad RIA. So Brian talked about Luciad Fusion, so we use that on the back end, but Luciad RIA is kind of the web-based front end. So this is, I'll just run a couple of demos here. Brian didn't show the fact that dynamic visualization is obviously very capably done by Luciad RIA. So just picking up from where you left off, Brian, here it is. So here's a very dynamic maritime data on the east coast of Canada that shows you all kinds of visual snail trails, but also talks about anomalies, right? So we loaded, I think, about 20 anomalies into the system, and one can kind of go through and you know, look at different anomalies that have been captured by Total Insight, and can play them back at their own pace and so on and so forth. So here you've got all the details. This particular vessel is interesting because in 2019 in April, it went into the St. Lawrence River, and there was a 10-knot speed limit that was put into effect there, but Total Insight kind of caught that vessel going over 10 knots for about an hour of time. This is to protect kind of the Atlantic whales as they were being, you know, hit by different boats accidentally and were dying unnecessarily. This is another more extensive demo that shows you Luciad, again, RIA front end that we demoed a couple of years ago down in the States. So here you're seeing kind of Total Insight fused tracks on the back end being visualized on Luciad RIA. And the nice thing about Luciad RIA is that it could run off a GPU on a laptop, really. So you can load tons of entities into it, and it wouldn't really lag or cause any of those delays from a visualization perspective and usability perspective. So you could do like live heat maps. You could bring it back to the icons if you wanted to. You could also do trajectories, these snail trails, which are really good for visual analytics. You already can form visually and notice kind of the traffic lanes that are being used in the Black Sea, which is where this particular event happened. You can kind of look at hotspots. You can kind of look at all those bright ports around the Black Sea and focus in on Odessa here on the top left there. Lots of you know, vessels that are just waiting to be you know, brought into Odessa for, you know, loading and unloading kind of shipments using tugboats. It'd be interesting to kind of run this on the Suez Canal blockade, or not blockade, but backlog that just happened. Brian just reminded me of that when he mentioned it. So you can kind of define your AOI and say, well, bring in all the anomalies. This was a data set that was run from April 2nd to April 16th, 2019. So, and this is all unclassified data, so we didn't bring in any classified data into this. So here you could see, you can filter based on anomaly type. In this case, you have doppelgangers, you have loitering, you have rendezvous, you have unexplained high speed, unexplained low speed. In this case, it was a rendezvous that was between two vessels. I'll just kind of speed ahead to the two vessels there. There they are. So there's the two vessels, and we bring in the track data within Luciadria, so one can kind of concentrate on this particular anomaly and play it back, as I mentioned, at their own pace. So here you could see kind of one of the vessels kind of goes up the river, the other vessel follows up the river, but that's not really where the rendezvous happened. Total Insight caught the rendezvous somewhere around here, where for about 3 hours, these two vessels kind of went in a circular motion. And the most interesting thing after that is that one of them kind of went eastward, and then the other one kind of went dark. So it turned off its AIS, which leads you to believe that some illicit operation is happening in that environment. So what happens next? That's kind of what total perception comes in. Total perception is a ModSim, a modeling and simulation framework that uses a different type of AI algorithm, multi-objective optimization algorithms, so that we can perform collection planning, mission planning, response planning, and so on and so forth. In the back end, we had to build a lot of models. So lots of subsurface models, surface models, air, space models in terms of platforms, and then sensors. We have to equip those platforms with sensors. You have lots of radar sensors. You have lots of AIS sensors. I just mentioned those, underwater sensors, and CBRN sensors. We just brought those on in the past year. We can take in vegetation, elevation data, weather data, as well as read in DIS in simulated exercise form. And in the end, what we want to do is automate and optimize data collection as well as mission planning. So remember that rendezvous that I just described in the north of the Black Sea. So what happens within total perception is that it, you throw it into total perception, it looks for assets that are nearby. Obviously, this is completely fictitious. There are no assets in that part of the world that we know of. But in other deployments, of course, the customer is able to plug in their dynamic and geolocational databases for their own assets. So here, there's a UAV that was launched from a nearby base. You could see the AI used kind of a snake pattern because it's trying to look for a dark target here. All those different red lines are detections upon the actual dark target using a sensor mode, sensor payload and mode that was configured by the AI. The total perception then catches actually the other vessel on its way back. So that's a bit of activity-based intelligence driven observations there. Total perception realizes that there's a couple of satellites that are going to come into view. So it tasks and queues off those two satellites. In this case, it was Cosmos SkyMed and TerraSAR X, with a couple of their sensor payloads, ELINT as well as synthetic aperture radar. 2 hits on each of the vessels again from space. After those are done, total perception realizes there isn't another satellite that it could reach in time, and we don't want to lose track of this dark target, so we want to minimize gap duration, which is one of the optimization objectives. So here there's an aircraft that's launched from a nearby base. This one's piloted, so you could see the AI kind of used a different pattern here. It's a loitering pattern because we know that the vessel is heading towards Odessa, and finally a maritime ship with a very high bandwidth radar tracked the vessel until it got to the Odessa. You may ask, how do you know it goes to Odessa? We have a deep learning trajectory predictor that's been trained on 6 to 7 years of historical data that provides us with our predictions up to 18 hours in advance. So if you kind of go back in time, you see this collection plan, all these red lines were from a UAV, space, piloted, as well as a maritime vessel, all in the hope that we can collect as much information about that particular dark target as we can. And that's what is called the high value collection plan, which has a high collection value, but a high cost along with it, so that you can acquire images and fly assets and a demand satisfaction of about 33%. There's also other collection plans that can come out of total perception, compromised ones, low cost ones, depending on the severity of the situation. Recently, we just integrated again with Luciad on the CBRN placement plans. So think of these environments where CBRN's chemical, biological, radiological, nuclear. Operators want to know where to place these sensors to protect areas of interest, or in this case, like downtown areas like schools and shopping malls and so on and so forth. So what we have here is we obviously have to model all the sensors in total perception, which we did, model the cloud particles, which we did, and now we have it. This was obviously a Google Earth video, but now we have it statically showing the Luciad, and next step is to dynamically show it in Luciad. So you can kind of see the different particles being tracked by differently placed CBR and sensors. But of course, in Luciad, which we've done the integration, you can see not only the fields of views, the cloud particles, but also you can measure kind of the cost that it takes to deploy a particular set of sensors, the coverage that you would achieve, and the protection that you would achieve upon the areas and points of interest. And of course, you have a kind of a low-cost solution, a compromised solution, and a high-coverage solution. Last but not least, Total Vision. That's where we apply our AI ML expertise to kind of imagery and moving imagery, video. So I won't spend a lot of time about this, but you know the gist. You've seen all the movies and all the demos. Here, what we want to do is detect, classify, and track people, objects, and events so that we can deter potential threats from committing harmful acts. So, I mean, we obviously compare to Cafe and some of the deep learning networks out there. These are all proprietary. We've trained these all on our own, built neural network architectures like RNN architectures for these tasks. So you can see here detection of motion, tracking of motion, classification. You can see kind of green versus yellow. Identification, you can see that on the bottom of the boxes with some license plate detection and potentially OCR scanning if the video is high enough. And of course, from a geospatial perspective, now there's lots of applications here. So one of the applications here in Canada is that we have these forest fires that come out yearly now, typically out on our west coast in kind of Alberta and BC, which are provinces that have lots of forestry. And the idea here is, can we use kind of machine learning so that we can detect these hotspots as they appear, right? So this is kind of a flyby, a drone flyby, and typically what is done is they'll kind of take all these different images and geospatially generate the metadata, and then when they come back and land, get all the data and then assess it and analyze it. But that just wastes a lot of time, and it's very human intensive and is not very reactive to where the hotspots are. So using our AI, you can kind of see that we're already kind of clustering, using machine learning, we can detect the hotspots and clustering together so that the authorities get alerted in real time upon detection of these various hotspots. So I know I'm limited on time. I think I took a bit more than 15 minutes, but here's the information. This is not my information, but this is Larus information. You can contact us on social media if you'd like, or just directly by email. I'll post my email onto the chat once I'm out of sharing my screen. Thanks, and looking forward to the discussion. Questions?